Hello everyone, engineering statistics and linear algebra. Today we do discuss sums of two independent random variables. Consider random variables w, x and y. Here x and y are two independent random variables. Example for this case is a noise associated with a signal here. Noise and signals are added. As a result, w will appear, but noise and signals, they are independent each other. In general, a sum of two independent variable can be represented using x1, x2, or else you can use y1, y2, z1, z2. Any notations can be used here. So if the two random variables are independent in nature, then obviously they are uncorrelated. As a result, a covariance of those two independent random variable will be 0. We have discussed that. If the random variables are independent, then obviously they are uncorrelated. As a result, correlation, covariance and correlation coefficient, they are one another same. Covariance equals to 0, then all values are equals to 0 here. For this case, let us prove that a variance of w equals to a sum of variance of x and y. This is the first derivation should be done by us. Second derivation is a PDF of w equals to a convolution of PDF of x and y. That should be done here. Here it is proved. PDF of a bivariate random variable w should be equals to a convolution of a PDF of x and PDF of y. It is the case because x and y are independent in nature. The third derivation, the characteristic function. Characteristic function of a w equals to a multiplication of x and a y, an individual characteristic function of x and y. These three derivations should be done by us today. Alright, first one, let us be prove variance of w equals to sum of variance of x and y. Given w equals to x plus y, apply expectation on both sides. So EW can be written as mu w, EX can be written as mu x, EY can be written as mu y. We know the definition of a variance in terms of w here. This is the definition. Substitute w is nothing but x plus y here, mu w is nothing but mu x plus mu y, and do the grouping x minus mu x plus y minus mu y. Alright, it is in the form of a plus b whole square. Use a square plus b square plus 2ab. First term, second term, and 2 into a into b. Expectation is a linear operator, so that apply expectation inside the bracket. Expectation of first term, expectation of second term, expectation of third term. Already we know that it is the definition of a variance of x, definition of a variance of y, it is the definitions of a covariance of x and y. And already we have said that if x and y are independent, its covariance will be 0. As a result, it is proved a variance of w equals to a sum of variance of x and y. Alright, let us show that a PDF of a bivariate random variable equals to a convolution of x and y. We have assumed that here x and y are independent. For this, we are in need of calculation of cumulative distribution function. We know the definition of a CDF. It is actually the probability between the range w and a calculation of a probability involves the region R. that region R is varying from minus infinity to plus infinity of x and minus infinity to the w of y. That region we have to consider here. So this calculation, this probability calculation, it is actually the probability over the range R here. That R region should be considered, within that probability should be calculated here. As a result, calculation of this thing is nothing but integration over the range R, and bivariate a PDF should be considered here. Alright, so consider the range. X is varying from minus infinity to plus infinity and y is varying from minus infinity to y. This point considered as a y. So using x plus y is equals to w, then that y can be replaced as w minus x. So you can observe this equation and this equation. They are one and the same. Its RHS equals to its LHS here, so that we can relate a CDF equals to this term that is written here. By comparing those two, this equation and this equation, I can write a CDF of this CDF of W equals to this term. All right. So we know the definition of a PDF. Actually, it is a differentiation of a CDF, differentiating this equation with respect to y, so that it becomes CDF becomes PDF, and this term differentiation and integrations are reverse process, so that it becomes cancelled, and this w can be replaced by this limit w minus x. As a result, this complete term can be replaced by this term, and a differentiation of CDF is a PDF here, that is written here. Alright, so we have said that x and y are independent in nature. So we know the property a bivariate PDF equals to individual multiplications of a PDF, that is used here. That is a property of a independent random variables. If two random variables are independent in nature, then a bivariate PDF equals to a product of individual PDFs here. So that a bivariate PDF is written in terms of multiplication of individual PDFs here. So what is this? This is the definition of a convolution. This is the definition of a convolution. So that hence it is proved. So this is the convolution integral. So this requirement is proved here, and also it can be written in terms of y. So this is the important derivation as a examination point of view. Hence it is proved. All right. Next, show that a characteristic function of w is a multiplication of individual characteristic function. So we know the definition of a characteristic function. So characteristic function, it is denoted as a pi, and it is defined in terms of e to the power j omega w, and we know it is a bivariate PDF of a two independent variable. Okay, so changing the order of the integration, that gives it is separated and written as it is, and make use of a change of variable concept. Let us put w minus x is equals to v. So if it is differentiated, we'll get dv equals to dw, and it can be replaced by v, and this w can be replaced by u plus x. So it is replaced here. U plus x can be written as e to the power j omega v into j omega x. That j omega x written here and j omega v is written in this case. Then what is this? It is a definition of a characteristic function of x. It is the definition of a characteristic function of y. So as a result, we can say that a characteristic function of w is the multiplication of individual characteristic function of x and y. Hence it is proved. Let us discuss a sum of uh, independent and identical distributed random variables. We have calculated mean, variance, PDF and characteristic functions of sums of two independent random variables. These expressions provides us with a method to analyze the sum of an arbitrary number of independent random variables. Specifically, we apply this method in the case when each random variable is the sum in the sum is related to the same PDF. The PDF associated with each xi is fx of x. In this case, denoted as independent and identically distributed random variables. Let us consider here a w is considered. Actually, it is a sum of independent variables. This summation is used here, and xi, where I varies from 1 to infinity. Can we call this as w is a sum of an independent variable? And what we have assumed in this case? In this case, we have assumed that each independent variable PDF is fx of x. We can take any number of random variables, assume that PDF of each random variable is the same. If that is the case, means they are called as independent and identically distributed random variables. W is considered, it is a sum of n number of random variables. In that case, a PDF of each random variable is same, so that they are called as and identical and independent and identically distributed random variables. All right, so in that case we have assumed that a mu of xi is equals to mu of x is equals to mu of x, and variance of each random variable is same, that is equals to sigma of x square. In all those cases, it can be any random variable, its mean and variance are one and the same. All right, so let us we write this equation as consider I and j. If I and j are same, for example 2 2 or 3 3, at that case they are multiplied each other, xi into xi, it becomes xi square. That is equals to, it is nothing but definition of a expectation, mu x square plus sigma x square. It is already proved. You can see the notes of first module, you can see this as a result. If I and j are not equal, for example this I can be 1 and 10, j can be 10, it can be 5 or it can be 6, at that time it is a multiplication. If this is a multiplication, means a mu of x, mu of xj. So it can be any random variable, its value is mu x only, so that mu x into mu x square. Let us limit our discussion when n is equals to 2. What happens here? If n is equals to 2, means only two independent random variables are considered here. Maximum value of I is 2 only. Then I is equals to 1, it will be x1, I equals to 2, it will be x2. At that point, what would be the value of expectation of w2? It is mu of x 2 into mu of x, because the value of this is mu x, value of this is mu x. As a result, we'll get 2 into mu of x. Then what about variance? Variance of this is will be sigma x square plus sigma x square. It will be 2 into sigma x square. When n is equals to 3, consider this as 3, not 2. Consider this value as 3 here. If this is 3, it becomes w3. Then 3 independent random variables are considered here, x1 plus x2 plus x3. Can we write this as w2 plus x3? Yes, it can be written. As a result, so mu of x plus mu of x plus mu of x, it becomes 3 into mu of x. And what about variance of w3? It is 3 into variance of x x. So in general that equation can be done as n can be any value here. You can take 10, 100 or 10,000. It can be anything. So in general it can be written as w of n is equals to w of n minus 1 plus xn. It is a general a sum of two independent random variables. And what about mu x? So a mean of that w is n times mu of x. If 10 random variables are calculated, if 10 random variables are considered, then mu of that will be 10 into mu x. Similarly, random variance, it can be n times the variance here. If n is 10, then variance of that sum of two independent random variable gives a 10 into a variance of x. So the PDF for WT is convolution of fx of x with itself, and PDF for W3 is the result of two convolutions. And the PDF for W in above equation is the result of n minus 1 convolutions. The characteristic function leads to, this is the case here. So PDF is how to calculate PDF of such case. It is if n is equals to only 2, then PDF of W2 is convolution of fx of x with fx of x here. If they are considered result of two convolutions. If n minus 1s are considered, and repeat the same thing. Then what about characteristic function? Characteristic function of a two independent random variable, where not only two independent random variable, it can be any number. As a result, characteristics function can be written as to the power n. So this is what the concept of IID random variables. So if you have any doubts, means feel free to ask me. In the next video we will see the next concepts. So don't forget to like, share, comment on the video, and please subscribe the channel. Thank you.